Presenter is Aaron Forde, who is also in MNT
10 minutes.
program.
20 minutes.
You better plan to finish 10 minutes. And I suggest that we make a group photo after all presentations. So he will be telling about new materials which are becoming famous and favorite for photovoltaics, so-called lead halide perovskites. Floor is yours.
Hello everyone, my name is Aaron Forde, and for the next couple of years my research will be involved looking at the charge transfer states for photo-excited transitions. So for my project I decided to look at the charge transfer states between lead halide perovskite and organic dye molecule. So motivation, why lead halide perovskite? So the biggest motivation is it shows a lot of promise for next generation photovoltaics for like dye-sensitized solar cells and thin films due to its well-aligned band gap, its high absorption of visible light, and its ability to transfer charge carriers long distances. So since it can carry charge carriers long distances, it can act as either an electron transport material or a hole transport material as well. So it's pretty versatile in that way. So then what we need to do is we need to find molecules to pair with it to extract either the electron or the hole out of it to do spatial separation of the charges so that we can run them through the circuits with the solar cells to get power. So for the models I use, specifically I use cesium lead iodine perovskite, CSPBI3. And then for the organic dye molecule, I just chose triphenyl nitrogen because it's the simplest dye molecule I could look at to begin with. And then for the input atomistic model for VASP, I chose a CSA-PB8I24 slab. So it's a couple unit cells that has a surface, and then it extends periodically into the structure to mimic bulk characteristics. And then we just place the dye molecule. It's not physically connected, it's just placed pretty close to the surface of the perovskite. And just to know that all of these conclusions, they are done at a ground state optimization, so it's all 0K, so there's no thermal fluctuations with these results here. So if we're looking at the spatial distribution of electronic charges, the right table shows the electronic transitions between orbitals I and J, so HOMO -2 to LUMO +8 state, and then the oscillator strengths for that transition, which gives the probability of that transition occurring, and then the transition energies, those transitions. So for this first one here, for the HOMO -2 to the LUMO +8, we can see that there's not much spatial charge separation because it's basically just jumps into another region of the perovskite. And that kind of makes sense that it has a high probability because when you look at the oscillator strength, it comes from the transition dipole, which is the oscillator strength is proportional to the square of the transition dipole. And the transition dipole is basically a measure of the orbital overlap between transition states. So it makes sense that the highest probability one would be spatially close regions for transitions. But then if we look at states that do produce spatial separation of charges, like our HOMO-LUMO state here, where the electron would reside on the perovskite and the hole would reside on the HOMO, we do get charge separation there, but it has a very low probability of occurring due to there's not much spatial overlap between the orbitals. They're on different sides of the materials, basically. So to summarize that, the most probable photo-induced electronic transitions occur within the perovskite, and they don't produce charge separation. While the transitions that do result in spatially separated charges, they have a very low probability of occurring. So we have to consider a different method to get spatially separated charges. So on the left, this shows the photo excitation from the HOMO -2 state, which leaves a hole to the LUMO +8 state where the electron would reside. And then if you think about it, that this is a very unstable state, and then the electron will want to come back down and try to get into equilibrium. And to do that, it will relax to the band edges, which happens approximately on the picosecond level. So if both the electron and the hole come to the band gaps, that will produce spatially separated charges. So to show this conclusively, I would have to do the charge transfer dynamics of this system as a next project to follow up on this. So in conclusion, photo-induced electronic transitions themselves are not enough to generate charge separation. We need to consider the relaxation processes after the photo excitation to the HOMO and LUMO gaps, where the electron would reside on the perovskite and the hole would be on the organic dye. So the organic dye acts basically as a hole transfer material. And then as a bonus, just a little simulation. As you can see, like the organic dye is it moves around a lot, and then the perovskite's very heavy, and if you look close enough, you can see some of the modes that move. And then for the next iteration as well, we would bind that molecule, place some functional groups on it, and bind it to the surface.
Okay, thank you, Aaron.